So let us do some more problems on Fourier transform. So this is the Fourier transform pair given, and we need to find the Fourier transform of 1 by 1 plus j2 pi t. If you remember, we have proved the duality property, right? Duality property. So what does duality property say? What does duality property say? According to duality property, if f of t has a Fourier transform capital F of omega, then capital F of t has the Fourier transform 2 pi del of omega, or 2 pi del of sorry, not del of, 2 pi f of minus omega, small f of minus small f of minus omega. So this one we have already proved in properties of Fourier transform. So instead of f of omega, I'll take omega is equal to 2 pi f. I'll take omega is equal to 2 pi f. So what will d omega be? D omega will be equal to 2 pi into d f. So I'll try and prove this property with not as a function of omega, but as a function of small f, right? Function of frequency, not the angular frequency, but the regular frequency. So I have my inverse Fourier formula, right? F of t is equals to 1 by 2 pi integral minus infinite to infinite capital F of omega. Instead of omega, I'm going to write capital F of omega means capital F is a function of angular frequency omega. Now I am going to write it as a function of f, my small frequency, right? Function of frequency f of f e power j omega t. In place of omega, I have 2 pi f t and d omega. Instead of d omega, I can write 2 pi df. So 2 pi df. 2 pi df. So 2 pi and 2 pi gets cancelled. Right? 2 pi and 2 pi gets cancelled. And what is this? This is nothing but, and now instead of t, I will write minus t. Instead of t, I will write minus t. So I have minus infinite to infinite f of f, capital F of small f, e power minus j 2 pi f t d f. Now I will interchange my f and t. So f and t I will interchange, right? Here, here, and here. So what will it be? F of minus f is equals to minus infinite to plus infinite capital F of t, capital F of t, e power minus j 2 pi ft df. This is nothing but the Fourier transform of f of t. Fourier transform of f of t. So if I change this the variable from omega to f, now what will the Fourier transform be like? My new Fourier transform will look like this: f of t according to duality theorem, my new Fourier transform will look like this. F of t has the Fourier transform f of minus f, right? The 2 pi and this 2 pi will vanish. I will have f of minus f. Now let me consider my f of t. This is my f of t and this is my capital F of f, right? Capital F of f. Now by duality theorem, what do we have? We have capital F of t has the Fourier transform f of minus f. So in this Fourier transform, in place of bf, I'll substitute t. So 1 by 1 plus j 2 pi t as the Fourier transform. What is the Fourier transform? Small f of minus f. Small f of minus f. So if I put small f of minus f, I'll have e power, in place of t, I'll put minus f, right? Minus f and u of f. So this is nothing but e power f u of f. So this is my Fourier transform for this signal. So that is how we can apply duality theorem, right? If we had omega here, we would have directly used this relations. Since we don't have omega, we have it in the form of f. I am actually deriving the or proving the duality property with f instead of omega, and then using the deduced relations. Whatever relations we have deduced, we are using it here to find the Fourier transform, right? So next problem, find the Fourier transform of the first signal is here, and this is the second signal, and this is x of t, and this is y of t, and we have a third question that is based on the first two, right? So what is the general form of this is the rectangular function, right? G tau of t. What is the Fourier transform of g tau of t? G tau of t Fourier transform with amplitude a, let us say, it is going to be a tau sampling of omega tau by 2, right? Here a is equals to 1, and what is the value of tau? Tau is what? The width of the rectangular pulse. It is, well, this is minus and this is plus. So the width is going to be from -1 to +1, that is 2. So let us just substitute these values here. A is 1 and tau is 2. So the Fourier transform for the first signal is 2 sampling omega. Tau is 2, so 2 gets cancelled. So this is my answer for the first signal, x of t, right? For x of t, this is my Fourier transform. So similarly, I'll find the Fourier transform for y of t, right? What will be the Fourier transform for y of t? The amplitude here is 1, and the width tau is equals to from -2 to +2, that is 4. So a is equal to 1 and tau is equal to 4. So a into tau, 4 sampling of omega. Tau is 4, so 4 by 2 is 2. So I can write it as 2 omega, right? Now I have to find the Fourier transform of this linear combination. So if I take Fourier transform of this function, f of 3 by 2 x of t plus 1 by 2 y of t, it is equal to f of sorry, I can write it as Fourier transform of 3 by 2 x of t, 3 by 2 x of t plus Fourier transform of 1 by 2 y of t. Now this is a constant, so I will get it outside. This is also a constant, I'll get it outside. So I have 3 by 2. What I have left here, the Fourier transform of x of t. What is Fourier transform of x of t? 2 into sampling of omega. So 2 into sampling of omega plus 1 by 2 is the constant, and y of t Fourier transform is y of omega. So y of omega, what is y of omega? 4 into sampling of 2 omega. So 2 gets cancelled. Here 2 and 4 gets cancelled. So my final answer is going to be 3 sampling of omega plus 2 sampling of 2 omega. So this is my final answer. This is the next problem. If f of t has a Fourier transform f of omega, then show that for real and even f of t, the Fourier transform is just the real part of f of omega. And for real and odd f of t, the Fourier transform is just the odd imaginary part of f of omega. So let us start that. Let us consider my f of t. F of t is a combination of real and imaginary parts. So f of t is equals to f r of t plus imaginary part. Imaginary part I'll call it as j into f I of t. Right? Now I'll find f of omega. F of omega. F of omega is minus infinite to infinite. In place of f of t, I am going to substitute this one, right? So I'll write f r of t plus j f I of t plus j f I of t into e power minus j omega t. E power minus j omega t, I will write it in the form of cos omega t minus j sine omega t dt. Right? Now I will expand or separate the integrals. I will write 4 different integrals. Minus infinite to infinite. First one is f r of t into cos omega t dt, and now I will multiply f r of t with minus j sine omega t, right? So minus j integral minus infinite to infinite f r of t into sine omega t dt, then plus j minus integral infinite to infinite, integral minus infinite to infinite f I of t into cos omega t dt. And here if I multiply the last two terms, plus j into minus j is plus 1, integral minus infinite to infinite fi of t into sine omega t dt. Right? Now my first question, for real and even f of t, when f of t is real and even, when f of t is real, first let us just consider real. When f of t is real, my this thing goes to 0, right? Imaginary part is 0. Imaginary part is 0, so this integral becomes 0. This integral also becomes 0. So I only have the first two integrals. And it is also even. When it is also even, what will happen? This is my even function. Cos is my even function. So even function into even function is always a even function, right? Even function into even function is a even function, and this is even function and this is odd function. So when you multiply even and odd, we get odd function, right? So how I can write this? The multiplication of this thing is a even function. So I can write it as 2 into 0 to infinity fr of t cos omega t dt. Now this is an odd function, fr of t into sine omega naught t. Even function and odd function, product of even and odd function is a odd function. When you integrate an odd function from minus infinite to plus infinite, this also goes to 0. So we are left with this one. So what is this here? It is just the real part of x of omega, right? Real part of x of omega. Real part of x of omega. Now we'll do the same thing for real and odd f of t. We'll do the same thing for real and odd f of t. Now when f of t is real, again this imaginary part goes to 0. Imaginary part goes to 0. This imaginary part goes to 0. So these two integrals are 0. Then what do we have? We have odd f of t. So odd function into even function. It is an odd function. When you integrate an odd function from minus infinite to infinite, it goes to 0. Whatever we left with, minus j, and this is a odd function and odd function. When you multiply both, we get an even function. So when you integrate even function from minus infinite to infinite, it's nothing but twice integral 0 to infinity fr of t into sine omega naught, sorry, sine omega t into sine omega t dt. That is nothing but imaginary part of f of omega, right? Imaginary part of f of omega. So this is the next Fourier transform. G tau of t minus 1 is just the shifted version of rectangular function. We know rectangular function g tau of tau has the uh, let us say it has the Fourier transform. Amplitude is not given, so I'm assuming amplitude as 1. So it has tau sampling omega tau by 2. Now I have to find the shifted version's Fourier transform. So g tau of t minus 1. That is the time shifted version, right? T minus 1. So what happens if there is a shift in time? We'll introduce a corresponding phase shift. How much phase shift will we introduce? It is going to be how much? E power minus j omega into, here it is 1, so into 1, right? So the phase shift is going to be e power minus j omega, e power minus j omega. The formula we used here is time shifting property, f of t minus b as the Fourier transform f of omega into e power minus j omega b. Right, this is the time shifting property. Let's move on to the next problem. F of t is e power jt f of t is e power jt for mod t less than 1. So how will we find the Fourier transform for such functions? You can do it in a regular way, minus infinite to infinite Fourier transform, right? So f of omega equals to minus infinite to infinite e power jt, right? E power jt, e power minus j omega t dt. Since t here is only in the range of minus 1 to plus 1, so I can change my limits from minus infinite to plus infinite to minus 1 to plus 1, right? I can do that. I can do this. Now I will integrate this. E power, this can be simplified as e power minus j omega minus 1 into t, right? Omega minus 1 into t. What is it, omega minus 1? Yeah, omega minus 1 into t. So if I simplify this, what will I get? I will get right. Now if I simplify this, if I integrate this, I will get e power minus j omega minus 1 into t divided by minus j into omega minus 1. Now the value limits for t is minus 1 and plus 1. So let me simplify. If I put t is equal to plus 1, I have e power minus j omega minus 1. If I put t is minus 1, I have e power minus j omega minus 1 into minus 1. So I'll make this plus. And in the denominator, I have minus j into omega minus 1. So this is nothing but e power j theta minus e power minus j theta, right? I can write it as e power j theta minus e power minus j theta divided by minus j omega minus 1. So I'll multiply and divide by 2. Right? Multiply and divide by 2. So what do I have here? This is 2 divided by omega minus 1, or let me not write omega minus 1 here. 2 e power j theta minus e power minus j theta divided by 2j. What is it? It is nothing but sine omega minus 1 sine omega minus 1 divided by omega minus 1 divided by omega minus 1. So this is nothing but 2 sampling of omega minus 1. 2 sampling of omega minus 1. This becomes plus, sorry. So it is 2 sampling of omega minus 1. Now let's move on to the next problem. F of t is cos pi t in the range of mod t less than 1 by 2. Mod t less than 1 by 2. Now let us, in similar way of the last problem, we'll do this. So f of omega is equals to integral minus 1 by 2 to plus 1 by 2 cos pi t. Cos pi t is nothing but, I can write, how can I write cos pi t? Cos pi t I can write as e power j pi t plus e power minus j pi t divided by 2, right? Divided by 2 into e power j omega t dt. Now I will integrate this, separate and integrate. 1 by 2 integral minus half to half e power minus j, or e power minus j. So there's a negative sign here, right? E power minus j omega plus pi, or omega minus pi. Like I should have omega minus pi. Omega minus pi t plus e power minus j to omega plus pi t, omega plus pi t dt. Then 1 by 2, I have 1 by 2, an integral of e power minus at. It is going to be e power minus j omega minus pi t divided by minus j omega minus pi plus again integral of this. So e power minus j omega plus pi t divided by minus j omega plus pi. The limits are minus 1 by 2 to plus 1 by 2. If you simplify this, we'll get, so first if you put t is equal to 1 by 2, I have 1 by 2 here, and when t is equals to 1 by 2, e power minus j omega minus pi by 2 divided by minus j omega minus pi, and in the second integral if I put 1 by 2, it is e power minus j omega plus pi divided by 2 divided by minus j into omega plus pi. Now I'll put minus 1 by 2 in place of t, so this becomes plus e power minus j or e power plus j omega minus pi by 2 omega minus pi by 2 divided by j omega minus pi into something. So again it will be plus e power plus j omega plus pi divided by 2 divided by j omega plus pi. So if you convert this into sampling form, finally, some more steps in between. If you convert that into sampling form, we will get 1 by 2 sampling of omega minus pi by 2 omega minus pi by 2 plus sampling of omega plus pi by 2 sampling of omega plus pi by 2 omega plus pi by 2. So this is my final answer. Alright, so now let's move on to the next problem. Sin AT by phi t. Sin AT by phi t. Now for this I'll apply duality. Right? Let me see how I can apply duality. Let me take g tau of t. The Fourier transform for g tau of t is a tau sampling omega tau by 2. Right? Sampling omega tau by 2. Now this one I can write it as, what is this? This is nothing but a tau sampling omega tau by 2. That is sin omega tau by 2 divided by omega tau by 2. Now here I'll apply duality. By applying duality, what will happen? By applying duality property or symmetry property, what will I get? A tau sin t tau by 2 divided by t okay divided by t tau by 2. We'll have the Fourier transform. It's going to be g tau of minus omega, right? It's going to be 2 pi into g tau of minus omega. So this is a even function, so I can write it as g tau of omega, and here tau and tau gets cancelled. So now I have 2a by t sin t tau by 2 on the left hand side and on the right hand side, okay, now this 2, okay, I'll write 2 pi into g tau of omega, right? G tau of omega. Now 2 and 2 also gets cancelled, right? 2 and 2 also gets cancelled. Now what is left? A by t sine t by sine t tau by 2 has this. This is the Fourier transform. Now let me take this pi to this side, the other side. So what can I write? I'll just erase pi on this side, and I will write it on the denominator here. Denominator here. I'll get it into the denominator side. So I have pi t in my denominator, and in the numerator I should have sine at, right? Now I will substitute tau by 2 is equals to a. So what happens here? A divided by pi t sine tau by 2 is a now. So at will have the Fourier transform. Now tau is equal to 2a, right? So g 2a of omega, g 2a of omega. And let me substitute a is equals to 1. I also substitute a is equals to 1. So what will happen? Instead of capital A here, I have 1. So Fourier transform of sine at by pi t, right? This is the same as this signal here is nothing but a rectangular function with width 2a. So it looks something like this. That is a rectangle function from minus a to plus a. That's all. It's an amplitude 1, right? That is my final answer. Now this one we have already discussed previously, so I'm not going to discuss this again. It's nothing but a shifted version of the rectangular function. So we have discussed this while discussing the Fourier transform of the standard signal of rectangular function, right? You can go back to that slide and check. Now we will see this signal. We'll see this question in the next class.